Welcome to this exploration of the physical vacuum. Researcher Valeriy Sbitnev proposes that the vacuum is not empty space, but a special superfluid medium. By modifying the classical Navier-Stokes equations, we can derive the Schrödinger equation, bridging the gap between fluid dynamics and quantum mechanics. The study focuses on two specific modifications to the Navier-Stokes equation. First, the viscosity is treated as time-dependent with a zero average. Second, an added term describes the quantum entropy gradient. These changes allow for the description of particles moving within a superfluid vacuum. At the end of the 19th century, physics faced a crisis as micro-scale observations contradicted classical laws. This led to the Copenhagen interpretation, which describes nature as probabilistic. However, Sbitnev looks back at de Broglie's pilot wave theory to find a more physical, deterministic explanation. In de Broglie's wave mechanics, a physical wave guides the particle along a specific trajectory, known as a Bohmian trajectory. This suggests that the particle does not simply exist as a probability, but is a physical entity being pushed by perturbations in an underlying medium, once called the ether. Recent experiments with classical oil droplets bouncing on a vibrating surface provide a visual analogy. These droplets induce Faraday waves that guide them through slits, creating interference patterns similar to quantum particles. This suggests that quantum behavior might emerge from similar fluid-like interactions in the vacuum. To build this model, we return to the fundamental laws of classical physics. Starting with Newton's second law, we apply it to a deformable medium. Leonhard Euler generalized these laws for continua, allowing us to describe mass density and force per volume within a fluid environment. The core of the Navier-Stokes modification involves vorticity, the measure of vortex motion. In a superfluid vacuum, vortex structures can emerge. These vortices represent the particles themselves, and because the average viscosity is zero, these structures can live for an infinitely long time without dissipating. While classical fluids lose energy to heat, Sbitnev hypothesizes that zero-point oscillations in the vacuum prevent these vortices from disappearing. The vortex exchanges energy with the vacuum's zero-point field, vibrating and pulsating at a specific frequency rather than decaying into thermal noise. Mathematical solutions show that these vortices have a core where velocity vanishes, similar to the eye of a hurricane. Outside this core, the velocity reaches a maximum before decreasing. This structure provides a physical model for the internal geometry of quantum particles like the electron. Interestingly, the radius of the vortex core is not static. It trembles. This trembling motion, occurring at extremely high frequencies, sheds light on the Zitter-Bevoging phenomenon. This refers to the rapid oscillatory motion of elementary particles predicted by the Dirac equation in relativistic quantum mechanics. By rolling up a vortex tube and joining the ends, we create a vortex ring. If the radius of the ring goes to zero, it transforms into a vortex ball. These dense, rotating balls move along Bohmian paths, perfectly simulating the behavior of quantum particles in a fluid flow. To derive the Schrödinger equation, we analyze the pressure gradient. In this model, the pressure consists of two parts, one related to diffusion and another to momentum transfer. Together, these terms form the quantum potential, a key element that distinguishes quantum mechanics from classical physics. When we divide the modified Navier-Stokes equation by the probability density, we reach a modified Hamilton-Jacobi equation. By substituting a wave function in polar form, we can reduce the fluid equations directly into the standard Schrödinger equation used in quantum chemistry and physics. This framework allows us to simulate complex experiments, such as fullerene molecules scattering through multiple slits. The resulting probability distributions create the famous Talbot carpet, an interference pattern that demonstrates how the superfluid vacuum guides even large molecules through a lattice. The physical vacuum is proposed to be a Bose-Einstein condensate made of particle-antiparticle pairs, such as electron-positron pairs. These pairs fluctuate within the first Bohr orbit, behaving as elementary vortices. This ensemble of vortices forms the superfluid fabric of our universe. Experimental research supports this view. For instance, rotating masses in a vacuum can induce a torque on distant objects, suggesting a vortex bundle can transfer force through the vacuum medium. This implies the vacuum has a fluidic nature that can be manipulated and observed. The model also incorporates Nelson's stochastic derivation of the Schrödinger equation. Nelson proposed that particles undergo Brownian-like motions due to collisions with subparticles in the ether. This chaotic movement, described by the Wiener process, leads to the emergence of quantum behavior from underlying randomness. We can interpret the quantum potential as a non-local correlation between the past and the future. The semi-permeable membrane of our present reality divides time, and the osmotic pressure within the superfluid vacuum helps maintain the stable trajectories of matter through this 4D space-time. Finally, we can imagine our world as a collection of baryonic and lepton droplets bouncing on a surface of dark matter. The superfluid vacuum acts as the dividing layer. In this view, dark matter divergence on a cosmological scale could be compared to soap spots spreading on water. In conclusion, the Schrödinger equation is not just a mathematical tool, but a description of a physical fluid, the superfluid vacuum. By understanding the universe as a special medium filled with long-lived vortices, we find a new path toward a deterministic and physical understanding of quantum reality.